Hey guys, hopefully a short lesson, hopefully mostly review stuff today. It's just kind of a review of the rules of exponents. Some of these I'm sure you learned, some of these maybe you did but you forgot. We're just going to talk about them. This should be, like I said, hopefully mostly review, we'll see. So when I talk about exponents, I'm talking about like a number. This A just represents any number, and then M and N represent any other two numbers, but they're the exponents. So A to the M times A to the N. We call this the product rule. I mean, that's just a name. We call it product because these two things are being multiplied. And the rule is when you multiply two things, when the base, this is called the base, by the way. That number is called the base. And that number is called the exponent. So I multiply two expressions where the bases are the same. I'll say that again. The bases are the same. You add the exponents. So this is A to the M plus N. A common mistake is that people will multiply these exponents. We'll get to that later. But for now, just know when you have the same base multiplied, you add the exponents, A to the M plus N. Here's an example, 3b squared times 3b. You could kind of rewrite this in a different order if you want, but you should just know that you multiply the numbers in front. 3 times 3, that's 9. And then b to the second times b. Well, b by itself is really b to the first. So b to the second times b to the first. We apply this rule. We get b to the 2 times b to the 1 is b to the 2 plus 1, which is 3. So this would be 9b cubed. I wrote that multiplication dot. Normally I wouldn't do that. 9b cubed. Same situation here. There's 1 times 2 is 2. And then I got a squared, a cubed, and a cube. That's 2 plus 3 is 8. 2m to the 8th. So that's how the product rule works. Multiply exponents with the same base. We add the exponents. Quotient rule. Unsurprisingly, when we have a product rule, it's almost always a quotient rule that goes along with it. Same situation, I have two exponential expressions with the same base. Again, this rule only works when the bases are the same. And the rule here is, when we multiply, we added the exponents. Here, when we divide quotients, we subtract the exponents. Pretty straightforward, I think. And the same thing, if we have two numbers, we just divide the two numbers. So 3 divided by 2 is 3 halves. And then p divided by p to the fourth, well, p is p to the first. So it's 3 halves p to the negative 3. 1 minus 4 is negative 3. You may already know that there's a way to rewrite a negative exponent as a positive one. We're going to get to that in just a minute. I might actually come back to this example. Come back. Because this kind of has some interesting things going on here. So here I do negative, there's a 1 here. Negative 1 divided by negative 2 is 1/2. And then m divided by m, well, that's just a 1. I mean, you can think of it like m to the 1 minus m to the 1. But m over m, they just cancel out, so you just get 1/2 here. It's not a very good example, to be honest, but we're going to come back to this other one in a minute. So quotient rule, pretty straightforward. Right, so negative exponents, like I just said, we saw those before. This is real important, and I think it is often forgotten. A negative exponent means 1 over the base to the positive exponent. So I did two things there. I changed it from a to the a on top, or the a by itself, and I moved this whole expression to the bottom of this fraction. And then I changed the exponent from negative to positive. So that's a way to rewrite this thing with a positive exponent. So negative exponents are like, think of them as like reciprocals. It's like 1 over. A to the 1 over positive n. Negative n becomes positive n. Here's a pretty straightforward example. I got 3 to the negative 2, so I can rewrite that as 1 over 3 to the positive 2, which is also known as 1/9. This is kind of an important one, I think, because when the negative exponent, it's already on the bottom. So I could do this. This negative exponent down here, I can rewrite as 1 over 5 to the positive 3, just like I did here. I wrote this as 1 over 3 to the positive 2. I can write this thing on the bottom as 1 over 5 to the positive third. And now I have this like complex fraction. I could think of the top as being like 1 over 1, and the bottom as being 1 over 5 to the third. And then the rules of fractions say that to divide these things, I flip over the bottom one and multiply them. 1 over 1 times 5 to the third over 1, which is 5 to the third over 1, which is just 5 to the third. So this is a way to do this. And for my way of thinking, it takes too long. There's like too many steps. So I think about it like this. A to the negative n is like a to the negative n over 1. I can write any number as anything I have, I can write over 1. So this expression here, I can rewrite just like this. And then this is going to be equal to 1 over a to the n, like we saw here. So like this negative on top becomes a positive on the bottom. And then if I think about rewriting this one, you can see that 1 over 5 to the negative 3 became a 5 to the positive 3 on top. So like you can really just kind of jump straight from 1 over 5 to the negative 3 to 5 to the 3. You can write this as, think about it like this. It's 5 to the third over 1, right? So like where before it was a 5 to the negative 3 on the bottom, it becomes a 5 to the positive 3 on top. So like what's actually happening here is if there's a negative exponent on top, you can rewrite it as a positive exponent on the bottom, and vice versa. A negative exponent on the bottom can be rewritten as a positive exponent on top, 5 to the third. So like, I think of it like if I see a negative exponent, it means that that exponential expression is on the incorrect side of the fraction. It's not incorrect technically, it's just where it is. But like if I want to make it positive, I got to put it on the other side of the fraction. So here the negative 5 to the negative 3 on the bottom becomes 5 to the positive 3 on top. And here a to the negative n, which is technically on top of a fraction, goes to the bottom. And if you remember it that way, it makes this whole process much, much faster. So I'm going to do this one and we're going to go back to that previous one. So I get me here, I got x to the negative 4 should be 1 over x to the 4th. And then y to the third is just y to the third. And I can rewrite this as 5y cubed over x to the 4th. Like this is 5 over 1, and that's y cubed over 1. So these things are on top. 5 times 1 times y cubed is on top. 1 times x to the 4th times 1 is on the bottom. So again, I think of it just like this negative 4th power means I should send this thing to the bottom of the fraction. And this y to the positive third power means it stays on top of the fraction. That's exactly what happened here. So to me, that kind of makes this process a little simpler. This is the rule right here. A to the negative n equals 1 over a to the n. That's the rule, period. But as far as like actually manipulating these expressions, like I did here and here, it's sometimes easier to think of this as being like, this needs to go to the bottom because it's negative. This needs to go to the top because it's negative. And then when they move from to the bottom or to the top, you see the exponents become positive again. So often we like to rewrite these things to positive exponents. Let me jump back to this one real quick. Like I said, this is 3 halves p to the minus 3. And that minus 3, like again, because there's no, this is not written as a fraction, you could think of this as p to the minus 3 over 1. And that negative means that this thing should go to the bottom as a positive. So it's 3 halves times 1 over p to the third. Remember, it goes to the bottom and it becomes positive. Then if you multiply these things together, you get 3 over 2p cubed. So I think it's easier to think about negative exponents as being on the wrong side of the fraction line. It just tends to make the calculations a lot easier. I don't want to have to go through all these steps every time to just get 5 to the third. I want to be able to say to myself, 1 over 5 to the negative 3 is just 5 to the positive 3. This is a pretty straightforward rule. Anything to the 0 power equals 1, with the one exception that a can't be 0. 0 to the 0 is undefined. That's the only time that this doesn't work. Otherwise, anything to the 0 power is always equal to 1. X, Y, Z to the 0, that equals 1. I don't really care what X, Y, Z is, assuming that none of these things are 0, of course. X cubed, Y to the 4th, Z to the 2nd over 11.72 Q to the 0, that's going to equal to 1. Anything to the 0 equals 1, except for 0. That's the rule. Don't forget this. What many of you are going to write later on is that 17 to the 0 equals 0. And I cannot express to you how much that's not right. You can't raise anything to the 0 power and get 0. All right? There's a reason why something to the 0 power equals 1. I'm happy to explain it to you if you'd like. I'm not going to right now. But just know that if you raise something to the 0 power, you get 1. Okay? Cool. Yeah, I'll just finish this up. This will be just one video. So there's kind of two parts to this power rule. The first part is this. If I have an exponential expression, a is the base, m is the exponent, and I raise that whole exponential expression to another power, this is when I'm going to multiply the powers. This equals a to the m times n. So a power raised to a power is like multiplying. Remember, if I have these things multiplied like this, and that's when you add. We call this the product rule. It doesn't matter what you call it, but this is the rule when you multiply. When you raise a power to a power, that's when you multiply the exponents. Multiplying the bases leads to adding the exponents. Raising a power to a power gives you multiplying the exponents. All right, so here, this is about as close of an analogy to this power rule as I could get. I have a base raised to a power, and then that whole thing is raised to another power. I multiply the exponents. 3 to the 5 times 4, which is 3 to the 20th. Same situation here. I have an exponential expression raised to a power, so I multiply the powers. -5 times 7 is -35. And you could rewrite this as 1 over y to the 35th. If I want you to write negative exponents as positive exponents, it'll say in the problem, it'll say, leave your answer with only positive exponents. If it doesn't say that, you can leave it like this if you want. I tend not to because this is harder to calculate with, but I'll tell you if I want you to do this, but I'm going to keep doing it just to show you guys how it keeps working. Last example here, same situation. A base raised to a power, and that whole expression is raised to another power. I just multiply the exponents. -3 times -7 is 21. Power is already positive. I'm good to go. This is the power rule, part 1, so to speak. And now the second part of the power rule says that if I have two things multiplied and I raise that whole expression to a power, it's like raising a product to a power. I distribute the exponent to the two things in here. So this is a to the n times b to the n. The power distributes to a product. This is a product, a multiplication. The power distributes to a product. There's a reason I just said that 5 times, and I'm going to tell you in a minute what it is. The power distributes to a product of things, a to the n times b to the n. The power also distributes to a quotient of things. So here I have a quotient, and the whole thing is raised to the n power. That's a to the n over b to the n. Couple of things to note here. Thing number 1, this rule does not work for adding and subtracting. I cannot express to you enough how much this is not true. Don't do this. It doesn't work. It also doesn't work for subtraction. Doesn't work. No, don't do this. Very wrong. That is false. You cannot distribute a power to a sum. You can distribute a power to a product. You can distribute a power to a quotient, but you cannot do it to a sum or a difference. The other thing I wanted to note was this. If I have something that looks like this is not the same as this. Like if there's no parentheses around it, like there is here, you can't assume that I'm supposed to raise that whole fraction of the power. Like if I have 1/2 to the 4, oh, that's an n. If I have 1/2 and there's a 4 here, this just equals 1 to the 4th over 2, which is just 1/2. But if I have 1/2 in parentheses raised to that power, I get 1/16, because it's 1 to the 4th and 2 to the 4th, and that's 1 over 16. But like unless there are parentheses, and like AB to the second is not the same as AB to the second. Like this, you have to assume here that only B is being squared and the A is not. Unless there's parentheses, you can't assume that they're both being squared. So here I have the parentheses, which is good. So this is the same as -2 squared times x squared. Like I can distribute the 2 to the -2 and the 2 to the x. You do have to remember that you're distributing the 2 to the -2 and not just to the 2. So it's this -2 times -2 is 4, +4. And then there's an x squared attached to it. We can also think about this when it's a squared, it's pretty easy. It's -2x times -2x. And -2 times -2 is 4, and x times x is x squared. So this checks out. And it makes me confident that I should be squaring the minus, because I can see when I write this expression like this, the negatives square and they disappear. Same situation here. I have a whole thing and it's raised to a power, so I can use this rule that says I just distribute the -3 to each thing there. So -3, I'm going to raise this. There's two -3s. That's confusing. I'm going to raise this -3 to this power. I get -3 to the -3rd. And I'm going to distribute the -3 to this x to the 5th. 5 times -3. Remember, we're multiplying. This is like that power rule, the power rule part 1, I guess, when you raise a power to a power. Let me just rewrite it all first. And then y to the -1 to the -3. So like I just distributed the -3 to each term inside the parentheses. I put it on the -3, I put it on the x to the 5th, and I put it on the y to the -1. And now this is really, this first one is 1 over 3 to the 1 over -3 to the 3rd power. I put this on the bottom and make it positive. This is x to the -15, and this is y to the 3rd. Again, when I raise a power to a power, I multiply the exponents. And now I can maybe start combining these things. This is -3 to the 3rd is -3 times -3 times -3, which is -1/27. X to the -15 is like 1 over x to the 15th. That's the negative exponent rule. And then y cubed is just y cubed. You can rewrite this whole thing as one big fraction just by multiplying all the bottoms and all the tops. And I get -y cubed over 27x to the 15th. This would be like a final answer for this problem. All right, so I hope that was helpful. The power rule, the product rule, the quotient rule. And then there's some practice problems here. Some of these are really difficult. Like this one's kind of complicated. There's a couple ways to think about that. Maybe we'll talk about that one in class. Some of these you should be able to do on your own, I would think. Number 8 in particular should be pretty straightforward. But let me leave these. Maybe we'll talk about them in class. I for sure want to talk about this one in class because there's like a kind of a technique that makes doing these easier. But yeah, we'll do that. Hope this was informative and not too boring if you already knew this stuff. And we'll see you in class.